Alright, here we are on 3.4, don't break the chain. Okay, so let's take a look at this, another math task helping us understand more about patterns. So, I'm sure we've all received a text or email with something similar to this. Hi, my name is Bill Waits, founder of the Super Scooper Ice Cream. I am offering you a gift certificate for our signature Super Bowl, $4.95 value, if you forward this letter to 10 people. When you have finished sending this letter to 10 people, a screen will come up. It will be your Super Bowl gift certificate. Print that screen out and bring it to your local Super Scooper ice cream store. The server will bring you the most wonderful ice cream creation in the world, a Super Bowl with 3 yummy ice cream flavors and 3 toppings. This is a sales promotion to get our name out to young people around the country. We believe this project can be a success, but only with your help. Thank you for your support. Sincerely, Bill Waits, founder of the Super Scooper ice cream. Okay, so obviously a chain email, right? So they rely on each person that receives it to forward it on. And most of us probably just, delete the email or the text or whatever and don't deal with it. But, think about if everybody actually did it, how quickly would that get out and to how many people? So we're using this kind of as a way to explore the patterns that we're talking about. So we look at this and it says on day 1, Bill Waits starts by sending his email out to his 8 closest friends. Okay? So day 1, send it out to his 8 closest friends. They each forward it to 10 people so that on day 2, it is received by 80 people. The chain continues unbroken. Alright? So, how many people will receive the email on day 7? Okay. Question 2, how many people will receive, oh, that must have been a typo in there, will receive the email on day N? Explain your answer with as many representations as possible. Okay. So, between question 1 and 2, they want us to figure out how many people on day 7. Okay. And they also want us to figure out day N. Whenever we see that day N, that N, obviously is a variable, but basically it means they want us to demonstrate it in any case. Okay, so we're talking about using our math models here. So we are looking at using those models to help us understand the situation. So we've got a table we can make. We've got a graph, a picture, an equation, and we have 2 types of equations, right? Recursive and explicit. So those are all the things I want to see us use as we're doing this. So take a few minutes, try this on your own, see how many of these math models you can actually come up with on your own, and see if you can figure out question number 3, how much it would cost during the first week. How much will he have spent? Alright, well hopefully you hit pause, took some time to do that. So let's start off probably with the easiest one. Let's start off with a picture. Okay, let's see if we can understand what's going on here with a picture. So, we've got Bill Waits. I suppose we should start with day 0. He was the only one that knew about it, right? He was the only one with the email. So we've got the 1 email coming out to us. So then on day 1, maybe give ourselves, says he sends it out to his 8 closest friends. Okay? So, actually, we're going to have to think a little differently here, aren't we? Okay, let's actually call that. So, day 1, he had the 8 closest friends, and he forwarded it to 10 people. So 80 people get it, and then they keep doing that. So every one person is forwarding it to 10 people. But on the first day, Bill Waits only sent it to 8 people. So let's start with that. Okay. We're going to call that our day 1. It's when he sent it out to 8 people, right? So 8 emails, and each of those they sent out to 10 people, right? So you can see obviously a diagram is going to be tough to make, right? Because that's only 6, 7, 8, 9, 10. Okay, so we have to do that for every single one of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, so for every single one of these, we're sending it out to 10 people. Okay, which got us 80 on that second day. So then each one of these would send it out to 10 more people. Each one of those would send it out to 10 more people. Can you see that drawing this as a picture is going to be pretty tough here, isn't it? And then each one of those would send it out to 10. So you can see that we're going to fill up our paper way too quickly. So picture probably not the best, but it looks something like that. Okay, with these being the other people. It's just I have to do it for every single one of those, and so I'm going to run out of space. Okay, so maybe a table would be better. So let's think through this. Okay, so at the start on day 1, send it to 8 people. Then on day 2, and I know this isn't matching up with your days. Okay, and this is people who received the email, right? But because day 1 was when he started, that's why we're putting it at 0. So what are we doing? We're timesing by 10, right? Because if 8 people, they send it out to 10 each, that's what we're doing. That's the pattern here, is multiplying by 10. So we get 80. So day 6 would actually be, our number 6 would actually be day 7, right? So timesing this by 10. So we'd have 800 times that by 10. 8,000 times that by 10. And we just keep going with that. So we get 80,000, 800,000, and then 8 million. Okay, when we keep multiplying everything by 10. Alright, so that kind of answers our first. So on day 7, we have 8 million people receiving this email, which, if you have any understanding of how many people there are in the world, there's actually only a little over 7 million, okay, is what they estimate. So on day 7, how many people? Pretty much everybody, and even some extra, an extra million people somewhere else. Okay, so how many people will receive the email on day N? So that's where we come into our models, right? So on day N, we could follow this to demonstrate that picture. We could use this table to figure it out. We could also try graphing it, right? So we'd have 0, 1, 2, 3, 4, 5, 6. Okay. Now the problem is these are really big numbers, right? So how am I going to graph this? Okay. Well, 6 is clear up to 8 million. That's pretty high up. So we don't really have a ton of space to do this. So it would look something like this. And I'm kind of just estimating. Actually, maybe we should come up with our equation first. But it would look something like this. 8 people that first day would be really low. 80 would be a little bit higher. 800, now we're getting up higher. 8,000, up higher. 80,000, even higher. Okay, and so it would end up looking, if we graphed it, it would look something like this. Okay, something like that. Now let me actually pull up on Desmos. I'll graph it, and we can see it from there. Maybe a better picture of what it would look like. So here it is. If we were to graph it on Desmos, notice these enormous numbers. That right there is 8 million. Okay, so this would be 10 million, 6 million, 4 million, 2 million, and so on. So see how quickly that shoots up, right? Definitely not a straight line. And there's that point, that's day 7, right? Okay, so just kind of better idea of what's going on there. Alright, so now that's 2 of the models, 3 of them actually. We've got the graph, that would show us what n is. We've got the table, would show us on day n. We've got the picture, the diagram, okay? So now, we need our equations, right? So, let's clear some space here. Gonna get rid of this graph here. Alright, so we've got the recursive. Remember, with the recursive, we always start out f of n in this case, because they wanted an n, is equal to, so the next number, say if we're going to 7, the next number is equal to the previous number, n minus 1, okay, which is shooting us back here. And then what are we doing? We're multiplying by 10. And where did we start? Well, at f of 0, we were at 8. Okay? So there's our recursive equation. That demonstrates what's going on here as well. Okay? That's another way to show, another model. We also can use our explicit. Remember, the recursive connects output to output. The explicit connects input to output. So we go f of n again equals, well, where did we start? We started at 8 people. What did we do to that? We multiplied it by 10. How many times are we multiplying by 10 till we get down to n? N amount of times. So that shortcut is of multiple repeated multiplication, I should say, is an exponent. So there's our explicit equation, okay, connecting the input to the output. Alright, so those are all the models that we can use to demonstrate this, okay? So we did question 1, we did question 2, so now here's our next question. So if Bill gives away a Super Bowl that costs $4.95 to every person that receives the email during the first week, how much will he have spent? Okay, well, if we look at this, okay, now there's kind of 2 ways to think through this. And really what these numbers are the different people, right? This is how many people on this new day received the text or email. Same with these. So really, if we wanted to figure out how much it would cost for all of these, we would have to add up every single one of them, which would be pretty easy to do, right? We would just end up with, because 8 and 80 is 88, 888 is 888, so 8,000 would be 8,888. So basically, we've just got this number, 8,888,888. Okay? That's how many people in that first week received it. On day 7, that's how many people had received it. Okay? That's why on number 1, we answer with 8,000. But on number 3, we're thinking through that many people, because each one of these people, once these 8 received it, they sent it on, they didn't receive it again. Now, obviously, in the real world situation, we probably would have some people receiving it multiple times. Okay, but this is kind of going where we're going with it. So each one of these people is going to be given that much. So we just multiply it, right? Multiply that together, and obviously we want to use a calculator because that's going to be a lot easier. So we'll type that in, 8,888,888 times 495. And we get this answer. So it would cost $43,999,995.60. Which, if this Bill guy's already got that much, why would he even be bothering working, right? That's how much he would have spent. Okay? So once again, if we look at this pattern, okay, this pattern that we dealt with, it's a geometric pattern, right? We're using multiplication. Could we model this using addition? We could try. The problem is, to get from one number to the next, we'd have to add by different numbers, which is what we can't do. So once again, that geometric pattern is able to mimic some things better than that arithmetic pattern.